Hello my friend, welcome back to You Can Do TV channel. The billet making process through the induction and high-speed continuous casting (HSMC) route incorporates advanced technology for efficient and cost-effective steel production. The process involves several critical components, including an electric substation with a power factor correction system, a steel melt shop shed, scrap storage, DRI, sponge iron, storage, load manager, and a furnace transformer. Continuous Casting Machine (CCM) process. The billet making process begins with melting and refining, where scrap and sponge iron are melted in induction furnaces and refined to achieve the desired composition. The molten steel is then transferred to a ladle treatment and tundish, ensuring a steady flow into the molds. Following this, casting and solidification occurs as the molten steel is cast through high-speed continuous casters, gradually solidifying into billets. Electrotherm has introduced an innovative direct rolling concept through high-speed casters, significantly reducing the energy consumption typically required for billet reheating. Conventional 6/11 casters are ideal for hot billet rolling, as they maintain a withdrawal temperature of 1,100 degrees Celsius, the highest in the industry, eliminating bleeding at the cutting point. Advantages of Electrotherm's high-speed casters. One of the primary advantages of this technology is enhanced productivity, with throughput reaching up to 24 tons per hour, strand, and a casting speed of 3.8 meters per minute at 110 SQM section size. Finally, billet cutting and handling ensures that the billets are cut to the required length and either directly sent for hot rolling or cooled for further processing. Additionally, energy efficiency is maximized due to the high withdrawal temperature, 1,100 degrees Celsius, enabling direct hot rolling and eliminating the need for billet reheating. The structural robustness of the process is ensured through a sand-blasted steel structure with anti-corrosive treatment and high-temperature paint, which enhances durability. Optimized cooling and shell growth is achieved through PLC-controlled secondary cooling automation with 3 cooling zones, ensuring higher shell thickness at the mold tube exit to prevent bleeding breakouts. The large bar forged rolled process is an advanced metallurgical technique designed to enhance the internal soundness, strength, and uniformity of special bar quality (SBQ) steel. This process begins with an as-cast ingot, which is first reheated in a soaking pit to achieve a consistent temperature. The ingot then undergoes multiple forging passes in a 3,300-ton forge press, applying uniform pressure along its entire length. This precision forging significantly improves the ingot's internal structure, reducing center porosity and enhancing overall mechanical properties. Following the forging stage, the semi-finished product moves to a rolling mill, where precise shape and size control is achieved. The forged rolled process ensures consistent weight, improved dimensional tolerances, and superior center soundness. This state-of-the-art manufacturing approach is trusted by industry leaders worldwide for its ability to produce high-performance steel, meeting the most demanding application requirements in aerospace, energy, and heavy machinery industries. The Tesker Model 740 is a powerful 2-die thread rolling machine capable of rolling parts up to 12 inches in diameter with 340,000 pounds of rolling force. Equipped with a 75 HP variable speed drive system, it ensures precision and efficiency. The machine features digital size control with cycle monitoring, allowing for accurate adjustments. The integrated 20-foot bar handling system facilitates material movement, while an integrated load balancing crane aids in spindle assembly and part handling. Push-button size control with an absolute size readout ensures ease of operation. Infeed thread rolling is a precise and efficient process used to form threads on large bolts by plastic deformation, ensuring strength and durability. Establish length and pre-roll blank diameter. Before rolling begins, the bolt's length and pre-roll blank diameter are carefully determined. Control of thread rolling speed. The Infeed thread rolling machine applies controlled pressure through rotating dies to gradually form the thread profile. Proper speed control is critical to maintaining consistent thread formation, preventing material defects, and ensuring smooth surface quality. Checking the threads. Once the thread is rolled, the first inspection step is to visually and dimensionally check the threads. This ensures proper shape, crest, and root formation, confirming that the rolling process has successfully formed full profile threads without defects such as laps or tears. Checking the pitch diameter. The pitch diameter, the critical dimension between the thread flanks, is measured using precision thread micrometers or ring gauges. Checking spec plan. Finally, the finished bolt is evaluated against the specification plan, including thread depth, major and minor diameters, and surface finish. The TM4000Y2 is a high-performance multitasking CNC lathe designed for bar machining, featuring upper and lower Y-axes for enhanced versatility. With an 8-inch main spindle on the left side and an 8-inch subspindle on the right, this machine provides optimal precision and efficiency. The left spindle operates at 18.5-15 kilowatts with a maximum speed of 4,200 minutes, while the right spindle delivers 15/11ths of a kilowatt with a speed of 5,000 minutes. This lathe accommodates bar workpieces up to 82 mm in diameter and supports a maximum turning diameter of 215 mm with a turning length of 800 mm. Its dual Y-axis configuration allows for precise machining, with the upper Y-axis offering a stroke of -50 mm to +70 mm and the lower Y-axis ranging from -50 mm to +30 mm. The inclusion of a 12-station turret enables efficient tool changes, while the rotary tool motor, 7.5-3.7 kilowatts, operates at a maximum speed of 6,000 minutes for enhanced milling performance. Designed with automation in mind, the TM4000Y2 supports an in-machine unloader and discharge conveyor, facilitating seamless workpiece ejection. The machine's space-saving structure, measuring 4,741 mm in width, ensures efficient use of floor space while maintaining high productivity. User convenience is enhanced by a 15-inch touch operation panel featuring Takisawa's TIWAP1 software, which simplifies programming through an interactive interface. The system supports easy program creation, simulation, and execution without requiring G-code knowledge. Forging. The process begins with forging, where a heated metal billet is shaped under high pressure. This step enhances the mechanical properties of the material by refining its grain structure, increasing strength, and improving resistance to fatigue and stress. The manufacturing process of the pre-finished shaft follows a series of controlled steps to ensure optimal performance and durability. Saw cutting. After forging, the material is cut to the required length using precision saw cutting. This ensures that the workpiece conforms to initial dimensional specifications before further processing. Quenching and tempering. The shaft undergoes heat treatment to improve its mechanical properties. Quenching involves rapidly cooling the material to increase hardness, followed by tempering, which reheats the metal to a controlled temperature to reduce brittleness while maintaining strength. The design incorporates elements of both a reel shaft, used for coiling and uncoiling metal sheets, and a generator shaft, used in energy production. Material testing. Comprehensive material testing is performed to verify the chemical composition, mechanical properties, and internal integrity of the shaft. Pre-turning. Pre-turning is carried out to remove excess material and achieve a near-net shape. This step reduces machining time in later stages and ensures a uniform surface for subsequent operations. Milling. Milling is used to create specific geometric features, such as keyways or flanges. This operation enhances the functionality of the shaft by preparing it for integration into mechanical systems. Finish turning. Finish turning provides the shaft with its final dimensions and surface quality. This process ensures tight tolerances and a smooth surface, which is critical for proper fit and function in its final application. Drilling. Precision drilling operations are carried out to create necessary holes, whether for mounting purposes or internal lubrication channels. This is executed with high accuracy to maintain structural integrity. Non-destructive testing, NDT. Non-destructive testing methods such as ultrasonic testing, UT, or magnetic particle inspection, MPI, are employed to detect any internal or surface defects without damaging the component. Packing. Once all quality checks are completed, the shaft is carefully packed to prevent damage during transportation and storage. Heavy machining of a rotor shaft requires precision, durability, and efficiency. Using the screw-clamped positive insert South Carolina 38, this process ensures high material removal rates with a cost-effective approach. The Duratomic TP500 coating enhances wear resistance, enabling prolonged cutting times while managing extreme heat. Machining is performed on a Poremba heavy-duty center lathe, 12 meters by 195 kilowatts, with specialized tool holders for both roughing and finishing operations. For super heavy roughing, the South Carolina 3809 RR97 insert is used on a 25.5-ton rotor shaft, achieving 58 meters per minute cutting speed and 34 millimeters depth per pass. For finishing, the South Carolina 3809 RR97 insert is used on a 20.8-ton shaft. These solutions provide secure and productive machining for high-grade steel and superalloys. Material selection and preparation. Bimetal band saw blades are manufactured from high-quality bimetal strips. These strips consist of two types of metal, An alloyed spring steel forms the body, while a high-speed steel, HSS, wire is welded to the top. This combination provides flexibility and strength to the blade while ensuring the cutting edge remains hard and wear-resistant. Tooth formation and heat treatment. After welding, the bimetal strip undergoes precision milling to form teeth. The high-speed steel forms the tips of the teeth, providing superior hardness and sharpness. Heat treatment follows, where the band is subjected to controlled heating and cooling cycles. This process hardens the tooth tips to approximately 69 HRC while maintaining the flexibility of the blade body, ensuring optimal mechanical properties. Tooth setting and inspection. To reduce friction and enhance cutting performance, teeth are set in a precise pattern to ensure proper kerf width. Advanced CCD cameras inspect and measure the tooth setting with an accuracy of 0.002 mm, ensuring consistency and high-quality output. Final processing and packaging. After thorough quality control, including testing for hardness, flexibility, and cutting efficiency, the blades are coated for corrosion resistance and packaged for distribution. These blades are then supplied in various dimensions and tooth configurations, suitable for different cutting applications. The Phil Synchromill F42 Machining Center is designed for high performance and economical machining of complex components, particularly those made from difficult-to-machine materials. It features multiple spindles and a highly dynamic feed system, allowing simultaneous multi-axis operations for increased efficiency. The machine ensures precision through rigid construction and advanced control systems. Workpieces are loaded, machined, cleaned, and tested within a fully automated process. Its modular design enables flexibility for various production requirements, making it ideal for industries demanding high accuracy and productivity in machining operations. Steel production at ArcelorMittal Huta Warszawa begins with scrap metal preparation. Recycled steel is carefully selected and processed to ensure high-quality input material. The prepared scrap, weighing approximately 100 tons per batch, is then charged into an electric arc furnace, EAF. Inside the steel mill, the furnace heats the scrap to a temperature of around 1,600 degrees Celsius, melting it into liquid steel. This process typically takes about 1 hour. To refine the molten steel, alloying elements are added to achieve the desired chemical composition, and impurities are removed. Once the steel reaches the required specifications, it moves to the continuous casting phase. The molten steel is poured into a casting machine, where it gradually solidifies into semi-finished shapes, such as billets or blooms. This process ensures a consistent structure and high-quality end product. The next stage is the hot rolling mill, where the solidified steel is reheated to approximately 1,150 degrees Celsius. At this temperature, it becomes malleable and is passed through rolling stands at speeds of up to 60 km per hour. The steel is shaped into final forms, such as bars or profiles, according to customer specifications. The production of forge fittings involves several critical stages to ensure durability, precision, and performance. The process begins with the selection of raw materials, typically carbon steel, stainless steel, and alloy steel bars or billets. Next, the metal undergoes heating and forging, where it is heated to temperatures between 1,100 to 1,250 degrees Celsius, 2012 minus 2282 degrees Fahrenheit. After forging, the components are machined using CNC lathes and milling machines to achieve precise dimensions, often within plus or minus 0.05 millimeters accuracy. This precision ensures that the fittings can be seamlessly integrated into pipeline systems without leakage or misalignment. This ensures a dense, defect-free structure that can handle high-stress environments. High-tonnage hydraulic presses, typically ranging from 1,000 to 3,000 tons, are used to shape the fittings under extreme pressure. To enhance mechanical properties, the fittings undergo heat treatment, including normalizing, quenching, and tempering. These processes improve tensile strength, ductility, and resistance to wear and corrosion, ensuring a final tensile strength of up to 850 megapascals. The forge fitting production industry is a vital segment of the metal forging sector, providing high-strength pipe fittings for industries such as oil and gas, petrochemicals, power plants, and shipbuilding. The global market for forged fittings is valued at approximately $8.5 billion in 2024, with an expected compound annual growth rate of 4.8% from 2024 to 2030. Finally, the fittings undergo non-destructive testing, such as ultrasonic or magnetic particle inspection, to detect any internal defects. The finished products are then coated, packaged, and shipped to industries worldwide. This growth is driven by the increasing need for high-pressure and high-temperature fittings in demanding industrial applications. With increasing global demand for reliable piping solutions, the forge fitting industry is expected to continue growing, particularly in regions like North America, Europe, and Asia-Pacific, where industrial expansion and infrastructure development drive market demand. The manufacturing process of heavy springs begins with the selection of high-grade steel bars, ensuring compliance with ASTM and DIN standards. These bars, with diameters up to 40 millimeters, are sourced for durability and strength. Once procured, the raw material undergoes an initial inspection to verify its quality and structural integrity. The bars are then processed to achieve the desired mechanical properties. Magnetic particle inspection, MPI, is conducted to detect any surface or subsurface flaws in the raw material. This ensures defect-free production and enhances the reliability of the final product. Using CNC coilers with a diameter range of 14 mm to 40 mm, the hot coiling process is carried out. The steel bars are heated to an optimum temperature, allowing them to be coiled precisely into the required spring shape. The coiled springs undergo both wet and dry grinding to achieve uniform end surfaces. Wet grinding removes surface irregularities, while dry grinding refines the shape and smoothness. Springs are subjected to heat treatment processes, including quenching and tempering, to enhance their strength and fatigue resistance. Scragging involves compressing the springs to their solid height multiple times to ensure they retain their designed load capacity and eliminate any initial settling. Both vertical and horizontal peening processes are used to introduce compressive stress, improving fatigue life and resistance to failure under cyclic loading. Quality testing is an essential step in the production process. Fatigue testing assesses the durability of the springs under repeated load cycles. MPI is conducted again to confirm the absence of defects after forming and treatment. Load and torque testing evaluate the performance characteristics, ensuring compliance with industrial requirements. The springs are coated with protective paint to prevent corrosion and enhance longevity. Additional refinements are made based on customer specifications to meet precise industrial needs. Gartle springs ensures that each stage adheres to strict quality control measures, producing heavy-duty springs with exceptional performance and longevity. The manufacturing process of Beta Tools combination wrenches is a sequence of operations designed to ensure the highest quality standards. The production begins with raw steel that undergoes dimensional, chemical, and metallographic analysis. These cut pieces are then subjected to shot blasting, where high-speed abrasive particles remove impurities, rust, and contaminants, providing a clean surface essential for effective forging. Once approved, the steel bars are cut into sections of appropriate length through a shearing process, ensuring uniformity and preparing the material for further processing. In the forging department, the cleaned steel pieces undergo heating and hot rolling. They are placed in an induction furnace and heated to approximately 1250 degrees Celsius, making the metal pliable and easy to shape. The hot rolling mill elongates the pieces and adjusts their diameters to match the exact metal quantity required for the wrench. After hot rolling, the metal is gradually cooled in a controlled environment to relieve internal stresses and ensure structural integrity. Another inspection follows to verify that the cooled metal retains the correct shape and dimensions before moving forward. A quality control check, known as the hot Pringle check, ensures that the rolled metal maintains its required properties before proceeding further. The next step is blanking, where the cooled metal pieces are cut into rough wrench shapes using high-precision cutting tools. Subsequent quality checks confirm that these blanked pieces meet dimensional and structural specifications. Tumbling is then performed to smooth the rough edges of the blanks using rotating drums filled with abrasives, improving surface finish and ergonomic handling. A high-pressure stamping process called coining follows, enhancing the final shape and imprinting logos and dimensional markings onto the wrenches. Multi-spindle drilling machines create precise holes where necessary, and broaching ensures the correct wrench profile and fit. Another tumbling phase further enhances smoothness and surface uniformity. A final quality check ensures that the wrenches meet all design specifications before finishing treatments. The final stage involves nickel-chrome plating, where a galvanic electroplating process deposits a thin layer of nickel and chrome to improve corrosion resistance and enhance aesthetics. The last set of quality inspections confirm plating thickness, surface finish, hardness, and overall compliance with international standards. After undergoing 10 rigorous checks and a total of 24 processing phases, the Beta Tools combination wrench is finally packaged and stocked, ready for worldwide distribution. The spoon and fork automatic production line operates through a series of integrated machines, including stamping, molding, polishing, and packaging units. Raw materials, whether magnetic or non-magnetic, are processed to achieve the required shape and size. The system ensures precise cutting, trimming, and surface finishing, maintaining high efficiency and product consistency. By optimizing workflow and reducing manual intervention, the production line significantly increases output while lowering labor costs. Each setup is custom designed to meet specific manufacturing needs, ensuring a cost-effective and reliable cutlery production solution. The forging process for a small 1 pound, 1 lb hammer involves several key steps to ensure durability and precision. It begins with selecting a high carbon or alloy steel billet, which is heated in a forge to around 2000 degrees Fahrenheit, 1093 degrees Celsius, until it reaches a malleable state. The heated billet is then shaped using a drop hammer or power hammer, gradually forming the hammerhead's contours, including the striking face and peen, if applicable. After shaping, the hammerhead undergoes trimming to remove excess material and is then reheated for heat treatment. The process includes quenching in oil or water to harden the steel, followed by tempering to balance hardness and toughness, reducing brittleness. The final steps involve grinding, polishing, and drilling a hole for the handle. Once the wooden or fiberglass handle is securely fitted, the hammer undergoes a final inspection to ensure quality before use in various applications. Axes are crafted using time-honored techniques that require years of expertise. Skilled blacksmiths at Holzbruck work in pairs, precisely shaping raw steel with a balance of force, coordination, and craftsmanship. The axe head is hand-forged at the historic Holzbruck forge, which has been in operation since 1697. Made from high-quality Swedish axe steel, each head is expertly tempered to maintain a sharp edge even after repeated use and sharpening. The same level of care is applied to crafting the handles, made from solid American hickory. Each handle is milled into a specific shape for its intended purpose. Finished axe heads are hand-fitted, thoroughly inspected, and paired with a custom leather sheath to protect the cutting edge. The chain manufacturing process at Timken Drives USA is designed to exceed industry standards, utilizing advanced engineering and high-quality materials. The production process begins with domestically sourced steel, ensuring superior quality and quick adaptability to customer requirements. Tooling plays a crucial role in manufacturing, with in-house design and maintenance ensuring precision and efficiency. A 500-ton Minster press forms heavy bars into link plates, while a Beeler machine creates precision bushings. The metal components undergo heat treatment to enhance strength and durability. To increase resistance to tension, the chain parts undergo shot peening, where small steel balls strengthen the surface, and belizing, which reinforces critical connection points. Tumbling smooths rough edges before assembly. The automatic assembly process then integrates 5 individual components into continuous chain lengths. To prevent initial stretching, a controlled preload is applied, reducing the need for customer adjustments. The final step involves hot dip lubrication, where the chain is immersed in high-temperature grease for lasting protection. The company produces various chain types for industries like food processing, mining, and cement, offering both standard and custom solutions with reliable service and rapid response capabilities. Manufacturing process. The manufacturing of stainless steel and carbon steel pipe fittings involves multiple processes, including cutting, bending, forging, heat treatment, and finishing. Plants equipped with induction mandrel machines, high-speed beveling systems, and hydraulic presses ensure precision and quality. India has over 500 medium and large-scale units engaged in this production, with advanced facilities in states such as Maharashtra, Gujarat, Tamil Nadu, and Punjab. India's stainless steel and carbon steel pipe fittings manufacturing industry is a crucial part of the country's industrial infrastructure, catering to sectors such as oil and gas, petrochemicals, water supply, and construction. With an annual production capacity exceeding 2 million metric tons, India ranks among the leading global producers of pipe fittings. Growth and market size. The Indian pipe fittings industry has witnessed significant growth over the past decade, driven by increased demand for robust and corrosion-resistant fittings. The stainless steel segment alone accounts for approximately 1.2 million metric tons per year, while carbon steel pipe fittings contribute around 800,000 metric tons annually. The market is expected to grow at a CAGR of 6 to 8% over the next 5 years, fueled by rising infrastructure projects and urbanization. Key machinery used in manufacturing. The industry employs a range of specialized machines for manufacturing pipe fittings. Induction mandrel plant, up to 24, used for seamless bending of pipes, enhancing durability. T-forming plant, up to 12 inches, ensures high-pressure fittings production. Elbow making plant, 4 to 20 inches, produces seamless elbows essential for piping networks. Shot blasting plants, 6 inches to 30 inches, cleans and prepares pipe surfaces before coating or painting. Electric furnaces for heat treatment, enhances mechanical properties of steel fittings. 1,500-ton hydraulic press, used for shaping welded fittings above 24 inches. Quality standards and inspection. To meet global quality benchmarks, Indian manufacturers adhere to stringent standards. The inspection process includes non-destructive testing, NDT, hydrostatic testing, and ultrasonic flaw detection. Advanced marking machines ensure traceability, while radial drilling and lathe machines add precision to final products. Major applications and export market. Stainless steel and carbon steel pipe fittings are widely used in sectors such as oil and gas. Around 40% of India's pipe fittings are supplied to this sector, where corrosion resistance and high pressure tolerance are essential. Petrochemicals and refineries, contributing about 25% of demand, requiring high-grade materials for chemical processing. Water supply and irrigation accounts for nearly 15% of production, supporting large-scale infrastructure projects. Construction and engineering represents approximately 20% of the domestic consumption. Indian manufacturers export nearly 30% of their total production to markets in the USA, Europe, and the Middle East. With government incentives and investments in technology, the export potential is expected to rise further in the coming years. Challenges and future outlook. Despite its growth, the industry faces challenges such as fluctuating raw material prices, high energy costs, and competition from China. However, initiatives like the Make in India program and infrastructure development projects are driving domestic demand. Technological advancements, including automation and AI-driven quality control, are set to enhance efficiency and global competitiveness. Pipe preparation. The process begins as the pipe is rolled into the pipe facing station, where its ends are cleaned both internally and externally. The pipe ends are then beveled to prepare for automatic welding. An inspector checks the offset and land to ensure proper alignment. Once approved, the beveled pipe moves into the preheat station, where induction coils heat the pipe ends to the required temperature. Welding process. In the welding station, the reach rod is inserted into the upstream pipe. The next joint of the pipe is moved into position and aligned. A spacer ensures a good fit by tapping the pipe with a hammer. The P450 CMT, cold metal transfer, welding bugs are placed on the pipe band, and the torch tip is aligned to deposit the CMT root pass. As this pass is deposited, subsequent weld stations simultaneously deposit their respective passes. Weld spatter and silica are brushed away, and the cap pass undergoes a visual inspection. Non-destructive testing, NDT. The completed weld is inspected using automated ultrasonic testing, AUT. A safety alarm sounds in case of an emergency stop. The scan results are displayed immediately, ensuring the weld meets quality standards. Surface preparation and coating. A closed-cycle abrasive blasting system is used to remove oxidation and contaminants from the pipe's surface. A powerful vacuum immediately recaptures the abrasive material, leaving the weld ready for coating. Fusion bonded epoxy, FBE, application. An induction coil heats the weld to the required temperature for coating application. The coating head is then placed on the pipe, and a timer starts when it begins its first revolution. Injection molded polypropylene coating. The extruder deposits a polypropylene coating over the weld. A controlled radiant heat process prepares the factory-applied coating for bonding. The radiant heat coil is removed, and the injection mold is positioned. Excess polypropylene is trimmed while still soft. Final processing. After trimming, the field joint is quenched and dressed. A polycarbonate shell is secured around the completed joint to protect it during the cooling phase. The spool-base pipeline fabrication process involves multiple stages to ensure high-quality, continuous pipeline construction for subsea applications. Corrosion-resistant and custom-engineered piping solutions across multiple industries. The pipe fabrication industry is a critical sector that supports industries such as oil and gas, power generation, water treatment, and construction. In 2023, the global pipe fabrication market was valued at approximately $5.2 billion and is expected to grow at a CAGR of 4.5% from 2024 to 2030. This growth is driven by increasing demand for customized piping solutions, advancements in automated welding technologies, and stricter quality control regulations. Fabricated pipes are manufactured using a variety of materials depending on industry requirements. Carbon steel is the most commonly used material, accounting for 70% of production, followed by stainless steel, 20%, and specialty alloys, 10%. Pipe diameters range from 2 inches to 48 inches, with wall thicknesses varying from SCH-10 to SCH-160, depending on pressure and temperature requirements. For high-pressure applications such as refineries, pipes must have a tensile strength exceeding 60,000 psi to withstand extreme conditions. The fabrication process consists of several critical steps to ensure precision and durability. Cutting and beveling are performed using CNC plasma cutters, achieving accuracy tolerances of plus or minus 0.5 millimeters. Welding is a key operation, with automated gas metal arc welding, GMAW, and shielded metal arc welding, SMAW, techniques ensuring weld penetration depths of up to 5 millimeters. Quality control is stringent, involving non-destructive testing, NDT, methods such as radiographic, RT, ultrasonic, UT, and hydrostatic testing, where pipes are subjected to pressures of up to 15,000 psi to detect potential defects. To extend service life, pipes are coated with fusion-bonded epoxy, FBE, or 3-layer polyethylene, 3LPE, which provide corrosion protection for over 20 years in harsh environments. The demand for fabricated pipes is driven by various industries. The oil and gas sector accounts for 60% of total pipe usage, particularly in transmission and processing facilities. Power plants require pipes that can withstand extreme temperatures, sometimes exceeding 900 degrees Celsius. The water infrastructure industry has also seen a surge in demand for large diameter pipes, greater than 36 inches, which has increased by 25% since 2020 due to growing urbanization and infrastructure projects. The VVER 1200 reactor vessel comprises multiple shell rings, each serving a distinct purpose. The support shell ring stabilizes the reactor structure, while the central shell ring, exposed to neutron irradiation, influences the reactor's lifespan. The lower shell ring and elliptical bottom head provide support for core fuel assemblies. The vessel, weighing 334 tons, has a service life of 60 years and operates at an outlet coolant temperature of 328.9 degrees Celsius. Manufacturing includes smelting and forging pearlitic steel, forming under a 15,000-ton press, mechanical treatment, welding, heat treatment, and hydraulic pressure tests at 4,251 atmospheres to ensure safety and durability. At Fundy Bronze, a leading foundry in Alagoas specializing in copper, bronze, and brass components, the manufacturing of bronze bushings involves several steps to ensure high-quality products. The process begins with material selection, choosing the appropriate bronze alloy based on the bushing's intended application. The primary casting method employed is centrifugal casting, ideal for producing bushings, tubes, and rings. In this process, molten bronze is poured into a high-speed rotating mold, ensuring a homogeneous and refined metallic structure, which enhances the mechanical properties of the bushing. The foundry utilizes both horizontal centrifuges for rings and bushings up to 32 inches in diameter and vertical centrifuges for those up to 80 inches. After casting, the bushings undergo heat treatment to achieve the desired mechanical characteristics, such as increased hardness and strength. Subsequently, precision machining is performed in-house using modern equipment, including machining centers, lathes, boring, and milling machines. This step ensures the bushings meet exact dimensional specifications and possess a smooth surface finish.